What if I told you there's a planet so far from its star that according to everything we know about physics, it shouldn't even exist? And it's not just far. It's 28 million miles into the cosmic abyss, orbiting a star so small you could almost hold it in your hands. Welcome to TRAPPIST-1H, the seventh and most mysterious planet in the TRAPPIST-1 system. To understand why this world is so baffling, we need to talk about scale. Our solar system. Earth sits comfortably about 93 million miles from the Sun, but TRAPPIST-1H orbits its star at just 5.4 million miles. Wait, that sounds closer, right? Here's the twist. TRAPPIST-1 is what astronomers call an ultra-cool dwarf star. It's so tiny and faint that its habitable zone, the sweet spot where liquid water could exist, is dramatically closer than our Sun's. In fact, all 7 TRAPPIST-1 planets orbit closer to their star than Mercury does to our Sun. But TRAPPIST-1H sits at the very edge of this system, receiving so little starlight that its surface temperature is likely around -100 degrees Fahrenheit. Now, here's what makes this planet impossible according to current models. When planetary systems form from spinning disks of gas and dust, there's a natural limit to how far out planets can coalesce. Beyond a certain distance, the material is too sparse, the gravitational pull too weak. TRAPPIST-1H defies this limit. It orbits so far out that traditional formation theories struggle to explain its existence. Some scientists suggest it might have formed closer in and migrated outward, but that creates new problems with orbital stability. Others propose it could be a captured rogue planet, but the chances of capturing a planet into such a perfect, resonant orbit with 6 other worlds seem astronomical. Literally, the TRAPPIST-1 system is famous for its orbital resonance. The planet's orbits are locked in perfect mathematical harmony. TRAPPIST-1H completes 2 orbits for every 3 orbits of planet G, 3 for every 4 of planet F, and so on. This delicate dance suggests the planets formed together peacefully, not with late additions. So how did H get so far out? The leading theory involves planetary migration during the system's early chaos. As the planets interacted with the remaining gas disk, they might have pushed each other into these resonant orbits, with H getting the farthest push. But this requires precise conditions that make TRAPPIST-1 system incredibly rare. What's even more fascinating is what this means for life. TRAPPIST-1H is likely an ice world, but if it has a thick atmosphere or internal heat from tidal forces, which are significant in this compact system, it could maintain subsurface oceans. We're talking about potential habitats similar to Jupiter's moon Europa, but around another star. The James Webb Space Telescope is currently studying the atmospheres of these planets, and TRAPPIST-1H presents the ultimate challenge. Its extreme distance means any atmospheric signals will be incredibly faint. But if we can detect molecules like water vapor or carbon dioxide, it would revolutionize our understanding of how planetary systems form and where life might exist. This isn't just about one distant world. It's about testing the very limits of our planetary formation theories. TRAPPIST-1H represents the edge cases that force scientists to rethink their models. Every time we find a planet that shouldn't exist, we're actually discovering that the universe is more creative and diverse than we imagined. The existence of TRAPPIST-1H suggests that planetary systems can form in ways we haven't even considered yet. It's a reminder that for every rule we think we've established in astronomy, there's probably an exception waiting to be found in the cosmic depths. What do you think? Is TRAPPIST-1H evidence of new physics, or just an extreme example of planetary migration? Drop your theories in the comments,